This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Welcome to the second hour. So, if you want to find out the slope of a tangent line at A, that's what we say, at A, you compute this limit. Okay? So what is at A, right? Well, here's a visual illustration. If you had chosen A equal 1 earlier, you would get a picture like this. You get a tangent line with a certain slope. Turns out that that slope would be 2, okay? Slope 2. But if you choose a different value of A, like 7, look at the picture. The line has a lot more slope, okay? In fact, the slope was 14, okay? If you're a truck, well, in fact, if you're a truck, you don't want to climb any of those two slopes. You won't be able to. Too much. But you would much rather be on that one, okay? To go up. To go down to. Sorry, excuse me. All right? But you do realize that if you change the base point, technical word, if you change the base point, if you change the value of A, you will change the slope. You can see it, okay? And the formulas will bear it out. All right? Now, for a subtle point that is not stressed enough, I think, is that after you write down this formula, you don't need to draw any more pictures unless you want to feel good about it. And you get a perspective of what I'm saying if you go back to historical texts before Newton and Leibniz and after. Before them, it was picture after picture, and the descriptions that you see written in texts are, well, you draw a picture like this, and then you draw a line from here to here, and then you see that this triangle does that. It is all geometry. And what calculus does for you is it makes all of that a thing of the past. You can now compute the geometry without having to draw a picture. And I cannot, well, I can tell you. In fact, I'm telling you right now how much of an advantage that gives you. You can compute slopes and can compute tangent lines, and you can compute anything you want without having to go through the pain of saying, well, you draw a picture like this, and you draw a line from this point to that point, and then you notice that the triangle that, and gone. With every gain, there is a loss. You do lose your visual intuition if you carry that too far, okay? And in fact, there are some people who are sick people who carry that too far. There's a guy, Lagrange, right, who wrote a book on celestial mechanics with apparently only one picture in it, and he wrote in the preface, this book has only one picture in it. And you could tell that he was very happy, okay? Not too fast, right? Not too fast. So we're going to definitely move away from pictures, but not to the exclusion of pictures. For the rest of today, we're not going to have pictures, okay? Because you do have to get used to doing the manipulation, the algebraic manipulation. It is important, okay? By the way, this quantity here, the slope of a tangent line, is what we call the derivative. So, oh, no, when you say the words the derivative, the light doesn't go off. It goes on. Not out, on, the derivative. And then there is light. And there's a special notation for derivative. You put a little prime, a little dash after the F. So you're going to read this in the following way. This is the derivative of f at A. Or you're going to simply say f prime at A. Or f dash at A. And everyone had their own notation. Leibniz had his notation. Newton had his notation. This notation here is by Lagrange. Sorry, I know I'm in front, but notation. Okay. It turns out that of Lagrange's notation, Newton's notation, and Leibniz's notation, the best one is Leibniz. The shortest one, well, there's Lagrange's and Newton's. They're equally the same. But the one that stuck was Lagrange's. We'll talk about why Leibniz's notation is better later on, okay? But let me tell you what Leibniz's notation is. Remember, we can rewrite this as the limit when h goes to 0 of delta y divided by delta x, the variation in heights divided by the variation in displacement in x. And so Leibniz's notation was this. Difference in y divided by difference in x. But this difference here is what he called an infinitesimal difference. Okay? A difference between two things that are as close together as you want, but it's not 0. Okay? When he came up with that, here's a little 2-minute philosophical remark. When he came up with that, and Newton had something similar as well, a lot of people said, oh, you don't know what you're talking about. How can two things be not 0, but as close to each other as you want? If you're as close as the other as you want, the distance between you is 0. I'm as close as I want to the wall, and I'm touching the wall, and the difference is 0. Right? You can't have something that is as close to 0 as you want, but it's not 0. But Leibniz's answer was, well, it works. And you cannot argue with that, really. You can argue, but you will lose. If it works, it works. Right? And it's that thing again, the thing that I said took a few centuries to realize. We're talking about a limit here. It is not 0. It's very close to 0, but it's not 0. And it's the ratio that cancels out. 0 divided by 0 cancels out to give you something that's okay, 14. Okay? I did mention at the beginning that the concept of limit was a concept that was only invented later to justify exactly this sort of thing. It turns out that Leibniz's notation is the best notation, but it takes longer to write. And in many cases, you want just a short thing, and you use this one. Okay? All right. So what's the name of the game now? The name of the game is write down a function that you like and write down a value for a that you like, and find the derivative. Oh, let's do that. Let's do that, because that's my idea of fun, right? There is some sort of perverse mind who likes to do that. So let's see. Favorite function. Well, perhaps this is not my favorite function, but it is, you know, top 10 maybe. I don't know. Oh, why does it have to be all about me? Give me a function. Give me an equation here, anything to do with x's and something you like.
Something I like.
Something you like, yeah. Not too easy, please, not too hard. Anybody can contribute. Go. Yeah. Why, he's...
Squared plus
Are you reading that from the book? X squared plus what?
4x.
4x
Plus 12.
plus 12. That all?
And a is equal to 3. That's all.
And a is equal to 3. So what you need to do is this. Okay? Here's what you need to do. Limit, oh, sorry. F prime at 3 is the limit when h goes to 0 of, I'm going to leave plenty of room here. Instead of x, wherever I see x, I'm going to write a plus h. And a is 3. So I'm going to write 3 plus h. Bless you. 3 plus h squared plus 4 times 3 plus h plus 12. Take away. Take away. Now I'm just going to substitute x by 3. So it is take away 3 squared plus 4 times 3 plus 12. And then I divide everything by h. Okay? So far? Now, again, when you see a limit, the first thing to try in your head, you don't have to write it down if you can avoid it, is just try to substitute the value of h by 0. And you get 3 squared, so 9, plus 12, plus 12. So this is 9 plus 12 plus 12, 24, 33. 33. Okay? 9 plus 12 plus 12, 33. 33 minus 33 is 0, divided by 0. So it didn't make any mistake. Okay, this is always going to be 0 divided by 0. Okay? 0 divided by 0, I hope that after I do the algebra here, something will cancel out. So you need to expand these and see that things do cancel out. Okay? So let's do that. Oh boy. Okay. I'm going to write, coming from over there, okay? Limit when h goes to 0 of, expand that, it's 9 plus 6h plus h squared plus 12 plus 3h plus 12. So this, oops, sorry, it's not 3h, it's 4h. Okay, so it's expanding this bit. Take away 9, take away 12, take away 12, and divide by h. Nine goes away with 9. 12 goes away with 12. 12 goes away with 12. And this is the limit when h goes to 0 of 6h plus h squared plus 4h on h. Now cancel h's. It's still 0 divided by 0. Limit when h goes to 0 of 6 plus age plus 4. And at this time, you can substitute age equals 0. 10. All right? No mistakes? Are you guys happy with the canceling? When it cancel? Yeah. Okay, now let's make it more complicated. Not because we want to complicate, but because... All right, okay. What's so special about 3? Why don't you do just A and carry out everything with A instead of 3? I mean, maybe it's going to be horrible, but you don't know until you try. So you have to try. Okay? So you go there and you do it. Now, if it works, if it's not impossibly complicated to do, you have an advantage. You have a formula that works for any age. Oh, sorry, any age, beg your pardon, any A. Right? So all of a sudden you can have a slope when A is equal to 3, A is equal to 1, A is equal to 7, A is equal to 20. Better, right? So try it. Try it and see. F prime of A is the limit when h goes to 0 of I'm gonna skip one little bit here. This is A plus age squared. A plus age squared, so it is A squared plus 2AH plus H squared plus 4 times A plus H plus 12 minus A squared minus 4A minus 12. All of that divided by age. Check it out. It is 0 divided by 0. I'm not going to do it. I'll let you do it. You hope to cancel stuff, and stuff very obligingly cancels out. A squared cancels with A squared. 4A cancels with 4A. 12 cancels with 12. Limit, when h goes to 0, see what's left. 2AH plus h squared plus 4h on h. It's still 0 divided by 0, but this time you can cancel h away. Limit, when h goes to 0, of, sorry, of 2a plus h plus 4. And at this time, you can replace h by 0. 2a plus 4. And you, I mean, look, it's up to you, but I don't think this was any harder than the one we did with the 3. Just because I used A instead of 3 didn't make it harder, okay? You have to carry more symbols, and maybe you really don't like a squared, but you'd like 3 squared. You're more comfortable with 9. My advice to you is, want a sublimation, get over it, okay? Because you do have to move away into the more abstract setting. It is good for you, okay? 2a plus 4. So that's one thing. We don't want to be plugging in particular. La, 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 la. I really like to hear the melodies you put in your telephone. It says a lot about your personality. Mine is like this. Tring, 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 tring. Boring. Anyway, you get a formula now. It doesn't matter which value of a, you can immediately tell the slope, even though you, in principle, can't even picture this. But I can tell you the slope of a tangent line without having to draw a picture. And for any value of a that you care to pick. There you go. Okay? That's 1. 2. If we're going to use a, why don't you just use x? Why come up with another letter that you don't need? So what we do is the following. If f of x is that, then f prime of x is 2x plus 4. Don't use a, just use x. And what it means now is, okay, if you want to know what happens when a is 3, just put x equals 3 here. All right? Okay. So far, so excellent. We're going to move up a notch now. And that's not going to be a small notch. That's going to be a big notch. Imagine the following, that now you get another function to do. You're going to have to repeat the whole work you've done, right? But that's silly. That's not how we work in mathematics at all. We want to save work. We don't want to create work. Okay? And so we do what we've been doing for centuries, for millennia, in fact. Okay? And we don't always do it, only do it in mathematics. You do it everywhere. Okay? Here's what you do. You figure out the derivative of just a few functions. You can't avoid that. These are going to be the simplest functions possible. It's going to be easy work. Okay? And then whenever you have a function that's more complicated, but built from those, you should be able to figure out the derivative of a complicated function from the ones you already knew. And so you don't have to be redoing the limit every single time. Okay? You see that there's a huge advantage here. Okay? All right? So the name of the game now for the next half hour is, if you have some simple functions and you've already done the work for the derivative of those, can you figure out the derivative of the more complicated stuff that, even though it is more complicated, it is built from simpler ones? What do I mean by built from? Let me close the door again. What do I mean by built from simpler ones? Oh, take a look at the one on the board. X cubed plus 2x plus 8. It's built from 3 guys. X cubed 2x, and 8. Built by adding in this case. Take a look at 2x. 8, there's nothing I can say, but take a look at 2x. That's built from two guys. 2 and x. And it's built by multiplying. Take a look at x cubed. X cubed is built from three guys. X, x, and x. And that is built by multiplying again. So if you know simple guys, this is x. If you know simple guys, and you know the rules for building, you might be home free. And you are, because we know what the rules are. Okay? So that's what we're going to be doing now. Okay? I am going to give you a bunch of formulas here without proof. I'm going to give you proof later. Today is only let's do it. Later I'll do let's justify it. Okay? So the formulas go like this. The derivative of a number or a constant is 0. I'm going to write it like this. If f of x is equal to c, constant, c is for constant, for all x, then f prime of x is 0 for all x. I'm going to justify, I said I wasn't going to justify them. I will justify this one, okay, by drawing the graph of a constant. The graph of a constant is a horizontal line. And a horizontal line has slope 0. Okay? A horizontal line is y equals 0 times x plus c. Slope 0. 2. If f of x is equal to x, then f prime of x is equal to 1. I'm going to justify that one as well. F of x equal x is a straight line. And the straight line is y equals to 1 times x plus 0. So the slope is always equal to 1. Okay? And that's what's written here. So far, so good? Okay. Now, you notice that I told you what to do if you have a constant and what to do if you have just x. Now come 3 rules that you should not forget. Rule 3, Rule 4, and Rule 5. Okay? Rule 3 says the following. If you add f and add g, or subtract, add or subtract, okay? And then you take a derivative, you can do the same work by first find the derivative of the f, then find the derivative of the g, and then add them or subtract them. So this is what I mean by finding the derivative of something more complicated from something less complicated, from the building blocks. Okay? Imagine that f and g are building blocks. Like x cubed is a building block. As 2x is a building block. If I want to find the derivative of this guy, I don't need to do the limit of the whole thing. That's what I'm saying. Okay? I can get by doing this one separately, which is simpler because it's smaller, right? Then doing that one, getting those two answers, and adding them. Some people laugh very loudly. Can you pick up their laughter in there? Yeah. I would like to think that they are laughing at how good this class is, but I can't say that. Anyway. Do you see what's at stake here? Avoiding doing this whole thing by doing smaller things first and then putting them together. That's what's at stake here. Okay? Rule 4. Let's say now that instead of adding, you multiply f and g. And then you take a derivative. Now, that rule goes like this. And I can only justify this rule later, all right? Not today, later. It is given by this formula. It has a name. It's called the product rule, or Leibniz formula. Okay? It took Leibniz, if I'm not mistaken, 15 years to find out the right formula. 15 years. Well, he had a lot of time. He was a busy guy. He was a busy guy. But let's see that it does deliver what I promised, okay? Think of f and g as simpler guys. Okay? So f multiplied by g is more complicated. All right? It's a harder guy to do. Okay? Now, if you multiply them, and then you're taking a derivative, you're asking for the derivative of the harder guy. Now, what this formula is saying is that it can be written in terms of all of the simpler guys you already knew. G by itself, no derivatives, simple. F by itself, no derivatives, simple. The derivative of f, presumably simple as well. The derivative of g, presumably simple as well. At any rate, simpler than that. Okay? Do you have to memorize that formula? If I were you, I would. But you don't have to, because you can bring formulas to the exam and stuff like that. Okay? But we're going to see this formula so often you will end up memorizing. That's the odds. Well, sum, subtraction, multiplication. What's missing? Division. So f of x divided by g of x. Take a derivative. And what's the formula? Now, as you would expect, the formula is the more complicated one. And it goes like this. You square the denominator. Don't take a derivative. Just square the denominator. And in the numerator, this is what you place. Take away right? And I'm going to let you verify the claim that, again, something more complicated is being written in terms of something simpler. All right? Okay? So I'm going to start using these and show you how you can build more complicated things from simpler things. x squared. Okay? Now x squared is x multiplied by x. Okay? So, what's the derivative? What is dy dx? I'm going to use the new the Leibniz notation just for a change. Okay? I want to think of this here as f and that as g. So this is f times g. And use the formula number 4 here, the product rule. Okay? So what is that? According to the product rule, this is the derivative of x. How much is the derivative of x? It's rule number 2 there. Am I moving too fast? You guys need a break? 1. Okay. 1 times the function g. So the derivative of f times the function g. So it's 1 times g, 1 times x, plus the f times the derivative of g. So this is x plus x. This is 2x. Okay? Now remember when we did the Leibniz example? No, I beg your pardon. The Fermat and Pascal example with x squared. With x squared. And remember that you gave me the value 7. Remember the answer we got there? 14. It's 2 times 7. 2 times 7. Okay? Let's do this one. We already know the answer is 2x plus 4, and we did it the hard way. Okay? So let's do it again. What's the derivative here? What's f prime of x? Well, according to this rule here, when you have a big sum, you can do each one independently. Okay? So that is going to be x squared derivative plus 4x derivative plus 12 derivative. So far? Okay. What's the derivative of x squared? Oh, gee, by golly, I already did it right there. The derivative of x squared was 2x. So this is 2x. Plus, what is the derivative of 4x? Well, we're going to have to do that one. 4 multiplied by x. If I take a derivative, what do I get? I'm going to use the product rule. Okay? What's the derivative of 4? 4 is a constant number. What's the derivative of a constant? 0. So this is 0 times x plus 4 times the derivative of x. What's the derivative of x? 1. So this is 4. Plus, what's the derivative of 12? 0, because it's a constant. Look, look, look. Oh, don't you feel like a warmth in you when you get the same answer in 2 different ways? And it's the same answer? Okay? One divided by x. Let's do 1 divided by x. pum 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 pum. 1 divided by x. I'm going to use formula 5, the quotient rule. Okay? So, according to formula 5, whatever I do, I divide by x squared because I get the denominator and square it. So whatever is in the denominator, I just go there and square it. And now bother with the numerator. The derivative of the guy that's at the top, the derivative of 1. 1 is a constant. The derivative of a constant, 0. So it's 0 times x, 0 times x, take away the guy in the numerator multiplied by the derivative of the denominator. The derivative of x is 1. So this is negative 1 on x squared. Guys, do me a favor. Do this one here. When you go back home tonight, wait until midnight, because this has to be done at midnight. And compute this derivative here using the limit definition, okay? Limit, when age goes to 0, of 1 divided by x plus age, take away 1 on x divided by age. All right? Right? And you have to get the same thing. And it won't be impossible, but you will appreciate this when you try to do that. Okay? You remember what they say when you go to the gym, right? No pain, no gain. You only feel the gain when your muscle is hurting. It's the same thing here. You will appreciate this when you try to do that. What the stuff that's here on the left of the board is, we're still missing one piece, okay? I'm not going to lie to you. But it is the basis of all of the scientific development of the 18th century that was based on mathematics. Anything that you did in science that needed mathematics depends on what's on this board here right now. Because people couldn't get by just doing limits. I mean, it wouldn't get nearly as far as, right? So it is important. Why 18th century? 18th century, 19th century, 20th century, 21st century, and I'm sure 22nd century, and et cetera, et cetera. That's it. We're still missing a few pieces, as I said, but okay. To finish today, I'll just point 2 things out. Shortcuts. If you're multiplying by a constant, you don't do anything to it. Okay? Now, in principle, you have to use the product rule, right? You have to use the product rule. But the product rule, when one of the 2 guys is a constant, is especially easy. Okay, let's take a look at the product. Oops, sorry, I beg your pardon. I forgot the prime there. Let's take a look at the product rule when the g is a constant. Okay? According to the product rule, this has to be the derivative of a function f times the g. So the derivative of f times the g times c plus the function f times the derivative of a g. But g is constant. The derivative of a constant is 0. So this, you don't have to be writing that. Okay? So that's a shortcut. If you just have a constant multiplying, forget about the constant. Put the constant in front and multiply and take the derivative of the rest. Okay? So before, when you did the derivative of 4x, okay? This was just 4 times the derivative of x, so it's 4 times 1. It's just 4. Okay? So that's a shortcut. It's an important shortcut, so write down this as an extra formula, formula 6. Okay? Last shortcut, and that's going to be a very important shortcut because it happens all the time. That's going to be formula 7. So let me explain this. If you want to find the derivative of x to the power 2, here's what you do. 2 multiplied by x to the power 1. So it's 2x. Oh, exactly what we found before, by the way. If you want to figure out the derivative of x to the power 3, it is going to be 3 times x squared. Okay? The exponent comes out multiplying, and you subtract 1 from it. Okay? If you want to take the derivative of x to the power 8, that's 8x to the power 7. Very convenient rule. And there is a beauty to its simplicity. Okay? Why is this rule true? I'm going to just give you the beginnings of why it's true. Okay? Look, I have done this before by hand. So we knew this. All right? How do I do x cubed? Well, x cubed is x times x squared, right? Okay? So I can use the product rule. One of the building blocks is x, which was an original building block. And the other building block is x squared that was not an original building block, but it became one after I did this. In other words, you are allowed to use building blocks that you've created from these, right? Okay? Now, exercise for you to take home and do. Check that if you use the product rule here, using your knowledge of the previous two guys, you do get this equation. And of course, once you get x cubed, you can get x to the 4. Once you get x to the 4, you can get x to the 5, because x to the n is x multiplied by x to the n minus 1. And then you get a machine, right? If you do the previous one, you can get the next one, and so on and so forth. Why? Did I say action-packed? I'm exhausted. I'll see you guys next Monday. Cheers.